I forgot to record all of that blabbing about it. So if you watch this later, you have to pause it and read it yourself. All right, moving on. So if I have this charged disk that was described, so we'll do our best to draw this washer that allegedly, we're going to be shooting something through the middle of that charged disk, right? So there'll be some mass here that will have some speed going through there. I could call this diameter here, we could call that diameter 1, and that's a 5 millimeter diameter. We could call this other diameter of the outer one, we'll call that diameter 2, and that'll be 3 centimeters. And there's some other distance, 20 centimeters that it's exiting in the gun there, and some other information. We were told the charge density was 3 coulombs per square meter. This speed was 107 meters per second. We were told the mass of this electron, of course it's a standard, it's not like they change at all. So we have all this, is our sketch of the critical parts of the puzzle here, and we just need to have a decent description there. So we've drawn a nice picture of that, and we need to figure out a few things. So where do you start a problem like this? Well, knowing that charge density, okay, is a charge per unit area thing. Okay? You were given charge density that's on something that has a surface area. Except you don't know what the surface area of this thing is, but you have enough information to figure out what the surface area is. So if it were a solid disk, it'd be easy. Pi r squared. But it's a solid disk that's got a piece cut out of it. A smaller solid disk cut out of it. So we have a way to do that. So the area, in this case, the total area of this particular thing would be basically area 2 minus area 1. Okay? Which is going to be, you could say pi r squared. That's our favorite go-to for a circle, but I was given diameter dimensions, so r is d over 2, so d over 2 squared is going to be d squared over 4. All right? So we'll have pi d2 squared over 4 minus pi d1 squared over 4. So that means our area thing could really be thought of as pi over 4 times d2 squared minus d1 squared. We could compute it, but we might as well save our rounding errors to the last step instead of carrying them around, letting them leak all over the place and end up being wrong. So inevitably, we don't want to compute along the way. That's almost never what you want to do. You want to let computations pile up to the latest possible moment and then do it all at once for rounding error. All right? Just basic good. So now we've specified the area part of this charge density thing. And one reason why that's important is because we're going to have to calculate the work done. All right? And the reason we're going to have to calculate the work done is because we need to get to this energy, the kinetic energy, which is where we're going to get speed. Okay, we absolutely have to get to that spot. So this is about finagling our way. This is one way to think about the problem-solving strategy from where we're at to where we need to go. And so, in general, the work kinetic energy theorem is going to give you some pay dirt in pretty much any problem. Because the work kinetic energy theorem applies to almost everything, okay? So with the momentum principle, these are two pillars of physics. You can pretty much solve any problem in physics from one of those two starting points. Okay, so we can rightly assume, the work kinetic energy theorem. But inevitably, whether you start with that thinking or not, you would get down to a point where you don't know what A is. And you would have to compute what A is. So I'm going to take it a particular route where we're taking the easy kills out in advance and then throwing them forward into the harder part, and then we could step back and go, what would have been, is there a better way to think it through? All right, so I'm sort of setting you up in that regard. So we can put a pin in that. We know what the A in our charge density is. Symbolically, we actually have all the information that we could actually have a number for that area. All right, and we'll see why this matters in a minute. So charge, this means that I can take charge out of this. So charge density was given to me, but charge wasn't given to me. I just specified a way to talk about the area, which will be pi over 4 d2 squared minus d1 squared. So now we have defined charge in terms of a given quantity and a series of known quantities. One thing you could expect, okay? You could expect, I need to know what charge is in problems dealing with electric forces, fields, potential energy. Duh. Of course I'm going to need to know something about charge. And if I'm not given what Q equals, I have to find out what Q equals by some other means. All right? And so I was given an easy shape that means I can compute its area, and I was given the charge density, which means I can work my way backwards to Q. I know in advance I need to figure out what charge is since I wasn't told what charge was. That would be one way that you could think about how to start this problem. I don't know that that's the best way, but we're going to build our way up to the best way and then step back and go, okay, what should I do in the future when I approach problem-solving situations? All right. So now I have Q in the bag. If I wanted to compute it, I could. All right? But now the problem wants me to know, is this electron going to get up to speed? Will this electron, under these conditions, get up to 107 meters per second? Either it will or it won't. And I have to figure that out. And right now, I don't know whether it'll do it or not because I wasn't given much more information. So I'm going to generate it to find out if I can even do this. And so what do I do? Good question. Glad you asked. It is generally true. Whoops. My pen, not a highlighter. Work equals the change in kinetic energy. And in this context, okay, we know that the work side of this thing is going to be force times distance, and the kinetic energy side of this thing is going to be how we might specify kinetic energy. So I'll just leave it as delta K for the moment, all right? Because I don't want it to carry all them symbols around. So force times distance. What force, what distance? Well, the force would be coulombs law, which specifies that there's this electron in the electron beam. Duh, it's given in the problem. There's this charge Q that I could substitute all that stuff in for. And this is going to be over the separation distance squared, which is from the exit of the gun to the hole that it's getting shot through. Well, that's the force part of this puzzle. But then there's the distance part of this puzzle. And obviously, that right there is going to cancel out. And if you were to pile all of the things in here, we could have that negative come out in front. We have a bunch of stuff over some stuff times some stuff. All right? But I oversimplify. So we'd have Coulomb's constant. We'd have that fundamental charge on the electron in the electron beam. We would have the charge density coming back up here to our definition of Q. And we could we'd have the 4 and the remaining D left over down there. And then there'd be all that stuff left over from above, D squared, D2 squared minus D1 squared. So I just wrote the work part of this equation. So a more sensible approach might have just been to start with the overarching principle. Okay? I need to compute work. And so why am I doing this? Well, most of the resources that you'll look up, they don't start with the overarching principle. They start with all the easy kills, assuming that you already understand the overarching principle, which is not a wise assumption when you're still in the introductory stage of that topic, which is what we're in, even though it's the second semester of this course. So you might start with work equals change in kinetic energy and lay it all out, and then you're going to say, oh, I need to know this, that, and the other, and I'm out. And then you'd go do the things we've already done, plus what we're going to do next. That's going to be your call, because different problem solvers have different approaches. That might make more sense to some of you, and what we're doing might make more sense to the rest of you. There's just no way of telling. Not an efficient way. So now I have the work side of this puzzle. All right, so I'm going to get me a clean screen here. So we know that work is change in kinetic energy. You probably don't have to write that again. But we had this minus KE rho pi over 4D times the outer diameter squared minus the inner diameter squared. And that's going to equal the change in kinetic energy, which I can just simply write as 1/2 mass times final speed squared minus initial speed squared. All right? We can essentially solve that for the initial speed squared. All right, so I'm going to skip a few steps here, trusting that you could have done this on your own, since you're all Calc 2 and beyond level students. All right. And so V naught's going to be the square root of all that stuff. Okay? So we can get that speed. So V naught, we go back to the problem statement. So it's on another screen because it was a long problem statement. So we're going to have 107 meters per second squared. The K constant, that hasn't changed in a while. Don't expect it to. We hope it doesn't, because that gives us faith in physics. The charge density was 3. I'm skipping out on some units now just because space. Pi, I'm just going to put that in there for now. Close enough. Or I guess it's not 2 times, but 4 times. 9.11 times 10 to the minus 31. So this is that mass of the electron. And we had 20 centimeters, which would be 0.2 meters. Right? And I kind of wrote that big and didn't leave myself any space to put in the difference in diameter squared. Okay, so we have all that in the computation, and unless I flimmed when I should have flammed, I get 5.71 times 10 to the 7th meters per second. So I'm pretty confident that the trons are flowing out into that gun at sufficient speed. Okay? So that's cooking. That's 57 million meters per second. Speed of light is 300 million meters per second. So this is a good electron gun. It's not as good as the one at the Large Hadron Collider, which is getting them up to 3 meters per second shy of the speed of light. All right? Takes a lot of energy to do that. So we done it. Okay? Now, had we started with the kinetic energy theorem, we said, all right, I'm just going to use this overarching principle that applies to anything moving under the force. So think about it. This is why this is a good way to start. So we're going to kind of retool the problem and just kind of compare our thinking strategies. This applies to everything that's moving because of a force, which is pretty much everything. Right? And so then we break it down. This is force times distance. So now we're just still coasting on prior knowledge, the math side of this. Which force? The electric force. That's the force we're talking about. So we know that we're talking about K and a product of 2 charges. We know one of the charges has to be an electron. The other one is something I don't know. It's that thing related to the charge density on the washer. Some separation distance squared. All right? And nothing has really changed over here. Still know the mass, but I don't know anything else. I know one of the speeds. Okay? So now I'm at a spot where I don't know this, and I don't know this. But I was given charge density was a known number, and I know charge density is defined to be charge per unit area. So this is where I go, oh, I can replace the Q with charge density times area because I can compute the area simply. This is probably a better way to start this problem than the way we started it. But the problem solver is the person who decides what the best way is. Inevitably, you're going to have to know, if you're dealing with charge density and you have enough information for area, you're going to compute the area. Symbolically or numerically, you're going to compute. You know you're going to do it. So whether you do it at the beginning or the end really doesn't matter much. Okay? So from here on out, nothing would change. Then we would move on to, well, area is going to be the difference of the 2 areas just like we did, and we would do the same thing. And that one maneuver in the problem, that was half of the pay dirt, was reconfiguring the charge, the unknown charge quantity, into a product of charge density and area. That was half of the puzzle, back in the other one. The other half of the puzzle is what we started with, or this page with, the work kinetic energy theorem. All right? So So that's it for that one. That's a relatively simple problem to work on. Any questions about it? All right, this next problem is going to involve the same overarching theorem, and we'll start with it. But it's deciding why to start with it. So the one thing that's probably the most important thing about the last one was, why should I start with the work kinetic energy? Because forces were producing motion. Bam. And then it's, you write out equations, and then it's a matter of which force, which distance, which mass, which inertia is getting a change in speed and position. That sort of thinking, right? All right, so here's a different thing. We want to trap auto emission particles. We want to use UV radiation to change them chemically. We know the charge of these particles here. So we can, the exponent stuff doesn't copy over well. Gotta change it. Knocking these auto emission things around. Average particle's got a speed of 900 meters per second, so it's cooking. Goes some distance, 15 centimeters. Negatively charged wire, so this is like a bug zapper except for auto emissions, all right? That wire's got a charge density on it. This is linear instead of area, all right? We know the distance, this, that from the other. So we want to design this thing. Need to know the speed that an average emission particle will have if it hits that detector, because that'll tell us about its energy, etc. All right, so I'm going to draw a picture. I have to go to a new screen. Basically, smoke aimed at wire detector. All right, it's a relatively simple mechanical system. So let's see. We've got some particle here that's got a velocity 900 meters per second. There's some detector that's in the way of a wire. Okay? According to the problem, there's 7 centimeters between the detector and the wire. And there is 15 centimeters between the starting point and the wire. So let's do this. We can call this point A, and we'll call this point B. Put that in so this thing's going to go from A to B. All right? Could have called it A to D. Whatever we want. So I think that suffices for the setup of the problem. And now we just need to work out how this thing is going to go for us mathematically. So let's start with the work kinetic energy theorem, which is a good idea because I know that there is an electrostatic force that is going to be influencing the motion of this thing that's already moving. So work is done on a particle and it will change its kinetic energy. Bam. Work kinetic energy theorem written all over this. So that's why we start with it. And in case you forgot, you're going to, work is also, because work was done over a distance, I'm going to have a difference, okay, of distances here. And there's going to be a so the charge I'm going to leave change in kinetic energy alone for a minute. So what is this QV this minus QV that? If you remember, I mentioned it during the other videos that we were walking through. Voltage is work done per unit charge. So charge times work done per unit charge is work. And there's work done at this location versus work done at this location, and the leftovers is the net work. So this this right here, this would be our work at A and our work done at B. So in the past, work was force times distance. All right? And so since voltage is work done per unit charge, I need to multiply by charge to get work back. Don't even care what the force or the distance is. Charge and voltage are my force distance products, so to speak. That's a little sloppy, but it works out that way. All right, so that was also in previous videos that we were doing. So now we could call this the final minus the initial kinetic energies, and we're concerned at what's happening at that final spot, so I'm going to leave it in K form for a minute because it's easier to write that than all the other stuff that comes with it. Remember the V's, the big V's on the right, those are voltage, not velocity. I'm going to try to draw my velocities for kinetic energy smaller so that it's clear. But that's the irritating part about this particular topic, is when we apply the work kinetic energy theorem, we're using capital and under lowercase versions of V. So you got to be careful that you keep that straight in your work. Hence why I'm sticking, another reason to stick with K. All right? But sooner or later, you must write these out. So 1/2 mass times VB squared, 1/2 mass times VA squared, plus this Q VA minus VD B. All right. And we want to get that speed by itself, so if we were to multiply everything by 2, divide by m, all right, and do a square root business, then we would get this speed that we're curious about to be in this form. So again, the squared VA is a speed, whereas the other VA, VB are voltages. And we would get something from that. Problem is, don't know what that is. Absolutely don't know what the difference in voltage is. We weren't given any information about voltage. So I have to find some other way to compute the voltage. All right? So we know what VA is going to be these are all constant, and I just computed that. So that to the 2Q. So back over in this this right here, I'll have to compute that, but I know it. This difference in voltage there is an equation that would apply here, and it's this one. So you would have seen stuff like this elsewhere in prior note-taking things. So I'm going to write out some stuff, and then we'll take a swing at explaining it. All right, so the work done, which is your difference in voltages, that will be a work quantity, the difference in voltages that some charged particle traverses, force that produced that displacement, is equal to this integral, which is the electric field, which is the force per unit charge, times some infinitesimal unit of distance. So it's essentially, what do I get? I get voltage. Because electric fields are forces per unit charge, times some distance would be force times distance per unit charge, which is work per unit charge, which is what voltage is. So you almost didn't need to hear much physics to know that. If you knew that the electric field was force per unit charge and work was force times distance, you have to know that the difference in voltage would have to be the sum of the work done per unit charge, which could be obtained by electric field in product with a displacement. And it's just a calculus version of force times distance. Work equals work. Force times distance equals force times distance. Voltage equals voltage. So ponder that. Now this other equation, we developed it elsewhere, but normally you'd think, oh, well, isn't the electric field kQ per r squared? Well, yeah, that's the Coulomb version of it. But you can also think of Q in terms of its charge density. And so lambda up here, this is the linear charge density. All right. And you may not recall, but the K constant, the Coulomb constant, is 1 over 4 pi epsilon naught. And so in this process, we ended up cutting that 4 in half, but we still have the epsilon naught. And then the Z is factored in as well. So this is a formula you would just look up or memorize in that regard. So we have, that's where that comes from. This has been in other lectures, so I'm not going to go too much farther with that. And so what we can do now is basically compute this lambda per 2 pi epsilon naught. All that comes out because they're constants. A dz per z is going to mean a natural log of z. And we're going to go from 15 centimeters to 7 centimeters. And so this works out to, if we go back to the problem statement, which you don't have in your view, the linear charge density was a negative 8 times 10 to the minus 6 coulombs per meter. 2 pi is what it is. Epsilon naught, 8.85 times 10 to the minus 12 something or others. Not as important. and we're going to have the natural log of 0.07 minus the natural log of 0.15. And so my VA minus VB, difference in voltage, is going to work out to be this really large 109,000 volts. So now that we have that piece of the puzzle, calculus stuff comes in handy. So VB will be this 900 meters per second squared plus, oh wait, I think Q is. So we can pretend that we did that out. The number here, I didn't write it out, but I didn't write out the computation. Forgot to do that, but here's what that would be. The Q times VA minus VD. And then 6 times 10 minus 9th was the mass of that thing. And I think, yeah, that's all that was underneath the thing there, and we get this 1380.7 meters per second. All right. So the twist on this one, work kinetic energy theorem, straightforward and simple. However, I needed to get at the difference in voltage through a novel way, and calculus was our savior for that particular maneuver. All right? So